Well, greetings everyone. This is Jyoti Dodia, and we have Nigel Griffiths on today. This is the 79th session in the Power of Work webinar series, and today Nigel's going to be covering POWER9 performance review for all scale-up and scale-out systems. So without further ado, over to you, Nigel.
Thank you, Jyoti. Yeah, we've already noted the fact that it says scale out on the top of this slide, and it should be scale out and scale up. It started off earlier in the year. We can see that we're at version 18. So rather a boring title, and we're going to cover a whole bunch of different things about how to get the best out of your POWER9 servers. And you can see a lot of caveats on here. This is not an IBM announcement and not an official statement or legal document. That'll hopefully let me keep my job. All right, because I do say a few outrageous things now and again. And so let's just get started. I'm not going to go through this, but there's a whole bunch of different things in here looking at things like the Spectre Meltdown. IBMers are not allowed to talk about Spectre Meltdown, so I'm going to talk about the Spectre Meltdown rPerf numbers, which I am allowed to talk about. Then we'll look at some unexplained things like the ranges on the rPerf numbers suddenly appeared. Look at problems with single-threaded applications. Then we'll be looking at energy scale. This is the technology that balances the how hot we are against how fast we're going, and sort of a little bit trade-off in there. And we're going to use the O word. The O word is overclocking. That I was banned from saying, but sometimes it's just impossible to get around it. You just have to say the word. Then we'll look at how do you actually get your servers hot so that they have to clock down. It can actually be quite tricky. And then how do we get better performance, and if you're migrating, some things you might want to do. Right, so let's move on and talk about things. Okay, so the other title of this could be Explaining the Numbers in the Power Systems Performance Reports. And this is the third one is out now. I checked yesterday. That is the August 7th is the update. This includes the E950 and the E980. Performance numbers. We'll be looking at those in detail on some of the odd things that we can find in here. There was an update. The second one came in as a little bit of an update. If you've got an S914, then the rPerf numbers went up about 6%, which is good. That's it. This S914, of course, is the bottom end of our range, really. So I tend to talk about the bigger boxes when I talk about an S924. I'm talking about 24 CPUs and things like that in there. Also, we're noting here that the S914, when it's delivered at default, it's set to dynamic mode of managing the gigahertz and the heat inside the machine. Rather than everybody else's, all the other machine servers are set to maximum performance mode. Now the S914 comes at a slower gigahertz rating by default. You can go in and change it, and we'll show you how in a second. That's because some of the S914s go into office environment, and if we go in dynamic mode, the fans won't kick up if you're getting hot and make too much noise for your office environment. If your S914 is in the computer room, then change it to maximum mode and you get extra 9% performance boost for free, and who wouldn't want to do that? We've also found with the Power 7 and Power 8 machines that we have a thing called power idle saving modes, where we can clock down the CPUs to save electricity. And everybody loves green issues and saving the green furry animals and the children, and we'll all learn to sing the same song or something. It turns out when we asked customers, do you use the power saving mode to reduce electricity, perhaps at the weekends or something? And nobody does that, nobody at all. That's because the technical people that decide, do we want to go fast or save electricity, don't pay the bill. And most people working in the computer room don't actually know who does actually pay the electricity bill, so they don't give a toss. So, moving on. So here we have, in the Power 8 numbers, we now have the rPerfs before you switch on the Spectre Meltdown fixes, and afterwards. And so we can actually do a compare and contrast of the effect of switching on the Spectre Meltdown bug fixes on the machine to stop that security violation. And if you do the maths, everybody had to cut and paste all the numbers out into a spreadsheet. They start doing the maths, and the average for the rPerfs, and I assume the same will be for the CPWs, is 5 to 6% difference in the performance. So you lose a little bit of performance. Now, 5 or 6% is below, it's noise level. We don't usually tune our machines to the last 5% of performance. If you've got some massive database engine that's critical for your business, you may actually you actually can measure 5 to 6% changes in your performance. And our initial reaction was this was, wow, that's really low. Because there was on the internet some people running benchmarks on other CPUs and getting like 30 to 50% performance hits. So 5 to 6%, so all the power guys went, phew, that's really good. And I think some of the differences are that the power ranging computers are built to run very large LPARs, and so we have a lot of superior engineering in here, so we can take thousands of interrupts per second, and we're into the millions of interrupts per second on some of our bigger machines, and still run our workloads at high speed, high performance, and reliability. So part of our engineering has actually paid off in keeping the effect of Spectre Meltdown to that sort of low number. And in red in here, actual percentages are application dependent, and your applications may be different. But the rPerf cocktail of workloads are pretty good, and but I'm not allowed to officially comment on the Meltdown Spectre numbers. That's all now at this website that's at the bottom of this page. Now, again, it's something that I think has been fairly well hidden from customers. We do get people asking about this. What happens if I switch on the fixes for Spectre Meltdown and the performance difference is large? How can I switch them off again? Now, the answer is you have to have the fixes in the firmware, so you've upgraded your firmware. And then you have to have the fixes applicable for your operating systems as well to get the security up to what you'd expect. And in here, in the ASME panels that I hope everybody knows how to get to from your HMC, if you open up the system config, JD, can you see my arrow on the screen now? I'm not quite sure if it's worth me moving it around. Are you there, JD?
Let me see. I am here. No, I can't see your arrow.
Okay, I won't wave it around then. That's not going to help. Was there a... No, oh, here we go.
Annotation?
Yeah, I was trying to... Okay, you can see that one.
I can't actually.
Okay.
Sorry.
Yeah, you can see that one.
Now I can, yeah.
Okay. So I can point at things. So you go into ASME, default admin, unless somebody's changed that. Up in here, you can system config, then you go down to Spectre Meltdown, Spectre, and Meltdown the speculative execution was the sort of generic name for these problems. And you have to power off the server. Then in this panel, you'll find an option to switch off the feature. Then you'll start up the server again. So it's a bit painful to switch this on and off, but that's how you can remove yourself so that you don't have any performance impact of switching on these fixes. And if you switch off the firmware by doing this, when the operating systems start up, they'll say, "Oh, I've got no firmware support for these for the security, so I can't actually do it either." So the operating system doesn't switch on the features. It needs hardware support to actually run the fixes. Okay.
A couple of questions, Nigel, on that.
Okay.
Should we just take those quickly? So the numbers that you were talking about, I don't know whether this was the slide or the previous one, but can we translate the same percentages and so on to IBM I numbers?
I don't know. And you'll have to look at the performance reports and see if you've got before and after CPW numbers. I would expect them to be very much in the same ballpark.
Okay, yeah. And then another one was to do with the ASME. Was there a typo in the ASME on point 2? The next.
Okay, well, I'll go looking for a typo and fix it up later on.
Okay, yeah, that's it.
All right, let's continue. Let's look at performance. So the first thing is, when you look at this report, I found it was doing my head in. Mixing up the Power 8 and the Power 9 numbers, and then I was making lots of mistakes and picking out the wrong numbers and all sorts of things. So I tended to put things in a spreadsheet and separate the Power 8 and the Power 9 numbers. And then we have, in Power 8, we have a single gigahertz rating that we expect the machine to run in, and on Power 9 we have this range, and it wasn't really well explained what that means until you come to a secret chart that I have actually found on the internet, but I reckon that 99% of people won't have found it unless they've been told where it is. But so we've got these power ranges in here, and how do we decide whether we're getting the top number or the bottom number, and which one are we using to get the rPerf number? And the answer is, well, it'll be the top one, but we'll look at that in a minute. So it's a little asterisk there, and at the bottom of the table, which can be 3 pages further down, it says the Power 9 frequency is expressed from typical to max, which explains nothing, in my humble opinion. How do you decide which one you're going to run at? Doesn't tell you at all. What's a typical gigahertz? I have no idea what that means. I understand max, that's the fastest we can go. But okay, so we're going to explain those in this presentation. We also get over in here, instead of 1 rPerf number, we now get 4. I presume that the ST there means single-threaded. I really like checking these things up and fully understanding them, but that's not documented, so let's assume that, which means SMT1. I don't know, logically, can you have simultaneous multi-threading of 1? But anyway, that's what I'm going to call it. And internally, we've had the rPerf numbers for different SMT, number of threads per core numbers, for a long time, and we didn't sort of generally share them. We got those out if we had to explain some performance to a particular customer having some issues, or trying to explain why we're using these particular rPerf numbers when moving up to your next generation of computer. But now they're actually publicly available, and then a lot of people start worrying about them. And we've already seen Frank asking us, whoa, the numbers look, rPerf numbers look low. So if you take the worst case of the worst case, then yeah, the Power 9 machines are slower. Okay. Oops, sorry, I've hit the wrong button. There we go. And worrying about these things is, I take sort of an analogy. I usually go for cars for analogy. If you take 2 cars, a small one and a big one, and you take out all but one of the spark plugs, so they've both got 1 spark plug left, and then you're going to compare the cars. And so what will the conclusions be? Yes, both cars are terrible. And that's what I think about single-threaded workloads. Single-threaded workloads are terrible workloads, and we've known this for 25 years. And if you've got a single-threaded workload, just remove it. It's not the way computers are ever going to work again. And if you can't change that, well, you've got the wrong application vendor that you're going to. Everything has to be multi-threaded these days, and it's only laziness in the developers or laziness in the IT department that's keeping us running some of these old single-threaded workloads. So I don't have a lot of sympathy for people, as you can probably tell, running single-threaded workloads. But if you want to get Mr. Pessimistic out of the cupboard, then yes, you can look at the Power 8 numbers in here for a single core of 151, and for the Power 9, nearest equivalent. Notice the gigahertz is very slightly down at the moment. Quite often we bring out an update to a range note with some slightly higher gigahertz in a year's time. But at the moment, 144, and so yes, it's 5% down, but this is single-threaded applications. So I've decided, well, that's pretty bad. Can I actually demonstrate that? And so I did a little micro benchmark. I ran it on Power 8, then I did live partition mobility, moving it on to POWER9 to see what happens to the number. Yeah, 8. Yes, 5%. Terrible. So here's my little special application called worms, or wiggly worms. You can see these AAAs and things on the screen. Here's the little worms wiggling around, sort of frozen in time. There's another one up here made of the @ symbols in here. But here you can see we're doing 135 worm movements per second. Now, this is a program that is compiled with no optimization. Otherwise, most of the program would actually disappear. And it goes through a big loop doing lots and lots of mathematics, big chunks of, add one to this, take one from that, multiply this by that, and those sorts of operations, integers and floating points. So if we're 5% slower, then we're predicting it'll go down to 125. The little caveat's already arriving in here. This was on a pre-GA release. I could do it again. I'm pretty sure it'll be exactly the same. So when we got to POWER9, it went up to 192, which is a 42% performance boost. Whoa! So don't worry about your 5%. You might find, like this little program, is going the other way. Now, Wiggly Worms is very unusual. It's tiny. It's probably sitting in the level 1 cache. So it's not benefiting from some of the internal bus bandwidth benefits of POWER9. It's the caching algorithms. It's not benefiting from that either. What it's benefiting from in here is the fact that the POWER9 machine does better in looking at branch prediction and using all the individual units inside the POWER9 processor at the same time. So if you have a program that's doing 4 integer math operations one after the other on POWER9, much more than POWER8 and POWER7, we'll actually all do 4 of those as long as there's not any dependencies in those mathematics. It will do them all in one clock cycle rather than take them one at a time. So it's using some side effect benefits of the POWER9 processor. You may well find your application will be going faster, even single-threaded. But on the rPerf cocktail of workloads, it goes down very slightly on the worst case of the worst case. So why anybody would run a POWER9 machine to run one program on one thread defies me. Okay. So have a experiment with even your worst case applications. You might be pleasantly surprised by what you get, but I'm not going to promise you anything on there. On the more optimistic in here, if we look at the difference between the S824 and the S924, we'll look at the enterprise machines a little bit later on. You can see, well, it depends who you are. If you're a techie like me, I say, well, that's 47%. If you're a German or a scientist, then it's 46.7656%. If you're marketing, it's actually 50%. And actually, marketing actually claiming 60%, would you believe it? Because they assume that on POWER8, most of the people are using SMT4, which is the default, not crediting technical people that they could actually switch on SMT8 if they wanted to. And so you get a bit of a boost side effect there as well. So it looks pretty good. 47% in a generational leap. This is a lot of performance, extra performance for your bangs per buck. So we also have to look at this energy scale. This is balancing the gigahertz and the heat. So we go as fast as possible without generating too much heat that could damage the computer or the server. So we're going to look at that next. Right, now there's a series of charts in here. It has discussions with the energy scale guys. We've actually got to deadlock, so I'll explain that in a minute. So this is not to scale, all right? Don't try working out in here that if this is 4 gigahertz, then this level here is at 2.1 gigahertz or anything. It's not to scale. But we have the idea of a maximum speed that we're going to run at. That's the highest gigahertz rating that we have on that performance review. We have the thing called power saving. This is the mode you can flip the machine into to reduce the gigahertz, reduce the electricity, and save some money, and save the green furry animals on the planet. We have this nominal in here, which is a fixed frequency that we can run the computer all day long. The maximum up in here is more of a variable, flexible frequency that will go up to maximum unless we get too hot, and then we can come down a little bit from there. And some very sort of paranoid people say, well, I don't want my computer going slightly slower one day than it did the previous day, even though it's faster than if we stuck it into the nominal. Some people don't like the variability of that, but that's a very unusual workload. I guess 0 gigahertz is when the guys switch off the server. So we've got these three things. They are much the same as in Power 8. So this is a reminder for Power 8 only. These are the terms that you get in Power 8. So when we're setting these things on the ASME, we have a thing called Disable All mode. That means disable all variable frequency modes, and this gives us the nominal frequency fixed. And we have the static power saver mode. As you see, that comes down, saves some electricity, and we have this dynamic favor performance mode, which runs at a frequency somewhere between the nominal and maximum. And this is where we got into some tricky problems with the thought police. These were called turbo and ultra turbo. Then the distinguished engineer said, well, that sounds like a boy racer turbocharging his car. We don't want to have associations with that. So we then had fast and very fast, and quick and very quick, and all sorts of things. And eventually they could not decide on a name. So I tend to call this frequency here the frequency with no name. Okay, let's continue on. So in Power 9, we have Disable All mode and Static Power Saving mode. Okay, and then we have a new one called Dynamic Performance mode. Remember, this was Dynamics Favor Performance mode. So it's now Dynamic Performance mode. And then depending on how busy the machine is, what gigahertz it will be running in. So if we're fairly lightly loaded and ballpark up to 40% or something, then it'll be running near this maximum gigahertz rating at the top. And as it gets busy, then the computer will get a little bit warmer, and so we'll slide down to the sort of medium, halfway between somewhere, not necessarily halfway, between maximum and nominal. And if you get very, very heavy workloads, you're running 100% flat out on all the cores in the entire server, then it will actually slide down and go down to the nominal gigahertz rating down in here. And this is pretty much what we had in the Power 8 mode machines as well. So there should be no surprises. That's what you're getting. And I'm trying to express by the thinner end of this wedge in here that only some of the time will actually be up in here, but the bulk of the time will be somewhere in between the medium and the heavy as the machine gets busy during the day with doing the primary workload. Then we have the maximum performance mode, and as we've seen, this is the one that most of our servers in the Power 9 range are set to. And by the shape of this thing, you can see that most of the time it's going to be up here, right up next to the maximum gigahertz rating in here. Even if it goes to medium busy, there's 60% plus medium level, that'll be up in here. And only if it gets very, very warm and very overworked will it actually slide down. And it doesn't go down to the nominal, it comes down to this frequency with no name. And to do that, keeping it up at this gigahertz, you can see down in here, good for lights out computer rooms where there's nobody standing around it, because it may increase the fan speed, which can generate noise in the computer room and does take a little bit more electricity. So we're most often up at the maximum gigahertz rating, but only if necessary, because we're hot, then we're going to slide down. And note, if the temperature of the room is above 27 centigrade, then the gigahertz may be reduced as necessary down to normal to keep it in a safe range. So if things are getting hot because your computer room air conditioning's failed, for example. Okay, this is the normal way we're operating our computers in here. Now, we're going to put a whole lot of caveats in here. So we also have this thing called idle power saving, which means if whatever mode you're in, if the machine gets unbusy, nice untechnical term, then it will slide down to this power saving mode right down the bottom in here. If you're in dynamic mode, if the socket goes idle for a fraction of a second, so you're talking milliseconds, then it will nip down to this lower frequency down in here. And if you're in maximum performance mode, if the whole machine goes idle for many seconds, and that is changeable on the ASME panels. The default is it's actually 4 minutes. Well, that's what it was on my machine when I last looked at it. So it can be a couple of minutes. It will actually then go down there. But this is only if you switch on idle power saving. It won't do this diving down to a lower gigahertz rating. And I've got a chart showing this later, very near the end, in fact. So most of the time, maximum mode will be right up here on that maximum number. Okay. Oh, I've already noted those too. Right. This is reminding the fact that the S914 comes in as a default different if you're not next to an operator or in an office or something, then you switch that over to maximum and be up with everybody else. And I went backwards, so let's go forwards. Okay. So here's my diagram. This is not to scale, all right? Don't people trying to say, oh, look at this graph, it dips there but straightens out at this point in here. But no, it's just me just drawing the graph. So for maximum mode, we're going to try and maintain that maximum gigahertz unless the temperature rises when we're getting very busy, in which case it will slide down, worst case down to the frequency with no name. On the dynamic performance, it will slide down a bit earlier because it hasn't got the availability of spinning the fans faster to add extra cooling, so the gigahertz will come down a bit earlier. Nominal is the fixed, of course, so it'll just run that gigahertz rating all day long, and power saving is to save our electricity. Okay. Now, the slope of this is completely arbitrary, really, or where this started for me, right? Don't go looking at this and say, oh, look at that, 77%. It's going to start cutting the gigahertz. No, it's nothing like that, and we'll come back to that. I don't want to leave you with false impressions or anything from that. Don't make these assumptions. Right, so how do we set this power mode? Well, we're talking power 9, so we've got our HMC for scale out and scale up, running 910 or 910 HMC software. So we've only got the new graphical user interface, the Enhanced Plus. So this is a particular machine in here, and down this list in here is the launch ASME, and here it is. Default is admin. The alternative is we can click on a machine. I've selected it by name, and then clicked on it, took the actions, the all views, and here's ASME, and again you get into it here, 2 ways in. Then you're going to look at for system configuration in here. And then we go down inside that, there's power management, which is a pretty bad name, in my humble opinion, given the fact we have power servers running power chips that use electrical power, and they're very powerful. There's 4 reasons for using the word power, and we're not quite sure what it means. When you dive into the actual one, it says power and performance mode. The mode, that's what we wanted to set. And here they are, all are. We've got disabled, we've got enabled static power. That's the power saving. Forced down and stay down. We've got the dynamic and the maximum. And you can see at the moment this computer is set to disable all modes. That's the nominal frequency. It's a shame that the name doesn't actually say what it does. Then we got the details down in here. You select the one you want, the maximum, and you hit the power off or restarting an L part in here. This is quite good. Okay, let's go to the next chart. This is a bigger to help your eyesight reading these things and read about them. You can see down in here, top performance, increased fan noises is possible. Okay.
Questions, Nigel. Sorry.
Okay, yeah.
So that was just a suggestion about the cruising speed mode. The unnamed mode could be named cruising speed mode.
Good
mode.
thinking.
The real question is, does the new Power 8 HMC also have the option to reduce the fan speed because it's extremely noisy?
When it starts up, it's extremely noisy. When it's running, it goes down a lot. What was the actual question?
Is there a way to have? Is there an option to reduce the fan speed on the HMC?
On the HMC?
Yes.
No.
No.
You could wear earmuffs. I've not noticed it being noisy on the new Power 8 HMCs, so I'll go and put my ear next to it at the time I'm in the computer room.
Mm-hmm.
I'll let you know. Is there a way to monitor the gigahertz and temperature? Well, I'm glad you've asked me that. We'll come to that later on. Okay, let's move on. Right, now we know this is Power 7 and 8, all right? We know we have 8 threads, and this is what it feels like is happening. It's not what's actually happening, but let's go with that. So the first thread over here seems to give you most of the performance of the computer. And then when you start using the second thread, you get an extra bit of performance, a percentage of it, of the first one. In actual fact, these are both running equally inside the computer, but the gain seems to be less than the original first CPU. And then you put in the third and the fourth, and you get a bit more of a jump. And then you add the fifth, sixth, seventh, and eighth. You get a tiny little bit of extra workload, and that appears actually if you look at the rPerf numbers in here. So if you're running a single-threaded and you get an rPerf number here of nearly 200, 197. And if somebody says, give me more power, the temptation is you give it another virtual processor, and it will spread the L power across 2 CPUs. And of course, if you do that, you'll get another 198 rPerfs with the extra CPU. The other option, of course, is making it or changing your application some way to make use of more CPUs. If you go from 1 SMT to 2, you get an extra 88 rPerf. So that's quite a bit less than the 197 at the top in here. That's why this is like 45% of the original amount of power you've got in your computer. If you then switch on the third and fourth, you go from 2 to 4, you get about the same again. So these two add up to be about the same as this one. All right. But when you go to the 5, 6, 7, and 8 ones, we only get 28 extra rPerfs, which is 10% of what you got in here by giving it a whole new CPU. So these appear fairly weak in this example, and you can see that this gives you this gives you an extra 45%. These two give you 44% extra, and then there's some bits in here. Now, 13% is free, so it's worth having, but it's not an awful lot of extra oomph into your application. Right, now how does that compare with a Power 9? Well, Power 9 looks like this, and these are proportional. All right, so you got the first one comes in, and then the second one's a lot more powerful. These two are about the same as this one, and these 4 in here are about the same as this one. I've got the actual numbers coming up on this slide in here. So we're running at just about the 200. I selected this one because it is almost the same number, so that's easier to compare. I don't have to do any sort of ratios or anything. And we then switch to SMT2. We're getting 70% more performance, or more oomph, horsepower. Then we switch on the third and the fourth one, we get an extra 65% in here, all right? And then we switch on these 4 other ones, that's going up to 8, we get another 60%. So this is a big jump of performance in the SMT. And if before we were working out that we went from sort of 1 to 2 over in here we're going from 1 to 3 times the performance in total. So this is a particular strength of the Power 9 processor. And if you're not kicking in this SMT strength, then you're not going to get the benefit, the full benefit of a Power 9 machine. We really do have to kick this in to get the benefit of a Power 9. So you've got to say, wow, that's a big jump in SMT performance. So how did they do that? Well, first of all, they shrunk this chip so that smaller distances mean we can go faster. Because it's smaller, we can double the transistor count. We got 8 billion transistors compared to 4.2 with Power 8. So it's nearly double the transistors. We boosted all the bandwidth between the CPUs and the memory to memory, and out to the adapters. They've all been beefed up. But then this is the fourth one, the bigger one. We've beefed up the internal components of the CPU that are used by the SMT. Now we've gone to the next slide. Jess Dutelli, who's one of the designers of the Power 7, 8, and 9 chips. I said, well, how did you do that? How do the SMT threads get so much stronger? And he said, that's a good point, Nigel. We haven't explained that to anybody. So he put this into a standard deck, and we've seen this going around the technical university for the last year. But the big difference in here is you can see it's actually fairly difficult to compare the Power 8 and Power 9 because they use different terms and different organization inside the processor. But you can see in here, these things are got ×2, so there's 2 of these units inside each core that are shared between the SMT threads. So if all 8 threads wanted to use this particular unit, well, there's 2 of them, so 2 threads in this clock cycle could use this part of the processor core, but the other 6 threads would have to wait until those first 2 got off, and then the next 2 could have used this particular part of the processor, and then the next 2 and the next 2. So it would take 4 instruction cycles for them to each access this particular bit of the chip. But these have been wrapped up to 8. So if you like, if every thread wants to run a load store agent, the load store is reading and writing from the processor to memory. If they all want to do that in the same clocking cycle, well, they can. There's 8 of them, so every thread, if you like, has got its own one. It doesn't have to wait for the other guys to get out of the way. So this is how you boosted up the SMT threads. So they're practically a core to themselves, if you like. They're not getting interference from the other guys. A whole bunch of things are in 2, which is still pretty good for a chip design. These are going up to 8 in here. There were some of these more esoteric ones down here that were 1. They've gone to 2. They're not used quite as regularly as things like branches or doing integer maths or compare operations, but they're still doubled up. And there's some of these double width load stores and things down here, they've been doubled up as well. So this is how they managed to get the threads that much faster, even without changing their gigahertz. So what does this mean? If you're moving from Power 7 or 8, sorry about my shorthand in here, to Power 9, then you should perhaps reduce your virtual processor count. This will force less cores to be used and more SMT threads to be used. And that will actually benefit, you will force the use of SMT and you'll get the benefit of your Power 9 processor, and I'm calling that thread harvesting. If you take VPs down on this particular LPAR, then those virtual processors are available for other LPARs, maybe one that's really struggling or you need to boost, or new workloads coming onto the machine. So that's if you're doing, moving up. If you're also doing LPM between the machines, then you actually want to reduce your virtual processor number after you've got to Power 9. And then perhaps you also want to recalculate your entitlements in here, bringing them down because you're using less cores, and that again frees up more compute power for other LPARs. Okay. So what is? Go on.
Question. So this is to do with running in modes. So if I run in Power 8 mode on a Power 9 system, will I also get the Power 8 SMT numbers instead of the numbers?
You're cutting out a little bit there.
I'm sorry. Can you see the? This was a question to me privately. If I run in Power 8 mode on a Power 9, will I also get Power 8 SMT numbers instead of Power 9 SMT numbers?
Yeah. Okay. Right. Let's try and separate those 2 out. If you're in Power 8 mode on a Power 9 machine, then some of the new instructions that appear in Power 9 are blocked out to you because we'll pretend that they don't exist, so that your application is unaware of the fact that you're on a Power 9 computer but running Power 8 mode. When you're on a Power 9 computer, you get the full benefits of the Power 9 processor. Its advanced speed and all these SMT thread enhancements are fully available to your application. And for the most part, when I'm saying SMT 1, 2, or 3, I'm actually using it in 2 different ways. I have to sort of confess. One is the mode you actually set your LPAR to, whether it is allowed to see SMT4 or SMT8. When you're actually running your workload, your operating system will say, well, okay, I can see that I've got 8 threads available, but I've only got 2 programs to run. I'm effectively going to only schedule 2 threads, and the other 6 threads are not being used at the moment. So there's 2 ways of using that as well. I hope that explained it. Okay, so yeah, sorry, in practice what it means, when we're upgrading or using LPM, we have to take those 2 factors into account. Right, now let's look at some numbers in here and use that. So I decided that there's too many numbers in here. Let's just look at the bigger box down in here, in particular columns. I'm not actually sit there worrying about how big the cache is. That's just sort of a side effect of upgrading. So let's bring all these together. And so let's say I'm on a Power9 S824, and I've got 24 cores on my machine into my LPAR, and so I'm getting a 285 rPerfs. The machine is 80% busy, running quite happily. Okay, so when I do an upgrade, where would I want to go to? Well, I've very carefully selected this, right? So remember, we haven't got enough threads to keep SMT8. Haven't got enough threads in here, so we're only keeping SMT2 busy. It's actually in SMT8 at the setting at the moment, but I could go from here to here. Look, this is practically the same number, so I'm going from 24 cores to 20 cores in Power9. So I'm getting the same rPerf number, so that's reducing the VP number will free up 4 CPUs as I do that, and we'll still be running 75% busy. But that's not really using the power of Power9, which is in this column over here. I mean, look, you can see the number is almost like double over here, right? So let's have a look at some alternatives. Now, this is 75% busy. If we go to this one over here, okay, the rPerf is down slightly, so maybe the utilization number will go up slightly. And now you'll see that I'm running 10 cores. Wow, I've gone from 24 in SMT2 to 10 cores in SMT8. That's a big saving. I mean, it's half, right? Less than half, and we're still running fine. So this is the way you're actually going to save money and use the power of your Power9 box. If you went from 24 here to 24 here, you'll find you'll get more rPerfs. The unused CPU time will go up, but that's not going to actually give you any of the benefits of your Power9 processor. Now I'm going to play the same similar game in here with the E950. So here's the Power8, and I've got a very similar one in here, down in here in SMT2, with similar sort of numbers, slightly up. Or I could pressurize it to go into SMT8 mode, use those threads, by coming down from 48 to 24 cores. Half the number of cores. Now that does take some guts. If I go back one, actually, yeah, it's a brave man that jumps to the Power9 bot and immediately takes the VP count down to 10. Right? Yeah, if you do it and you get away with it, let me know. And even with this little drop in here, I make a note in here. If you went to 11 cores, you'd have the same rPerf number. So that does take guts, but that's where you should be heading when you actually upgrade to your Power9 machine. So there's a similar sort of argument in here for a Power9 E950. I've got another example in here. If you're in an SMT4, again, we could come down to here somewhere between these two of 36 SMT using 4 threads per core. But if we went to 8, then we could bring it down to up in here 24, from 48 to 24. That's saving a big chunk of your computer that you can use for other things. And I've got another example up in there as well. Okay, if you're using less cores to start with, there's some other examples in here. Right, let's look at the E980 in here. So this sort of thing, you look at it for a long time, and it suddenly dawns on you what's going on in here, because they're not explaining what's going on. If we look at the E980 in here, this is the one that has the CPUs that have, there's 4 CPUs in each KEC, and so it has 48 CPUs. There's 12 cores per CPU. So this is one range of 1 KEC, 2 KEC, 3 KECs, and 4 KECs in here. And you'll notice in here there's an extra column for this machine, the LPAR size. So this is a 48-core machine, single keck, and the LPAR is occupying all 48 CPUs, and we get an rPerf rating of 1200. In this one, we've got 96 CPUs, but the LPAR size is still 48. So we actually have two LPARs of 48, one on each keck. And then down here is 3 kecks and 4 kecks, and the same down in here. And this is why these are mathematically calculated with a slight variation on the end there. There's a 0.1 of an rPerf missing. Because in this bottom case in here, we're running 4 kecks, the largest machine configuration, and 4 LPARs, one on each keck. Now, my immediate point is that's cheating. Now, their argument back to me was, well, there's very few people that run 192 core LPARs. There are some, and we can give you a rPerf rating if you run the entire machine as 1 LPAR, but that's quite rare. It doesn't happen very often. People are, 48 CPUs is quite normal. Some people go to above that, maybe 64, in which case you're going to have to spread across two kicks in here, and you'll be getting a number. But most people are actually using smaller LPARs on these giant machines, down in the sort of 8 to 16 sort of range, lots and lots of LPARs. So bear that in mind when you're looking at these numbers in here. They're slightly different. So an LPAR sizes are not necessarily the whole server where they are for the other computers. Okay. So let's do a similar sort of calculation again. If we take the biggest Power 8 box here and compare it to a 3-keck version of the Power 9 machine, then the Power 9, even going down, taking 1 keck out, is actually going faster. So that's good size, 25% less cores as we upgrade. If we look at here, 1 keck in here with 48 CPUs and 1 keck in here with 32 CPUs is giving you the same performance, again with 25% less cores in here. So we can see the performance boost we're getting with our E980. But if we're again looking at workloads that are only using SMT2, then you can see in here, this one, we've got a similar number up in here, if it's SMT4, then all the green ones down below are about the same or going to be faster on the Power 9 machine, which in this case is practically everything. Right? And this is the big end version of the 48 cores. Okay. So again, we get similar sorts of workloads in here of upgrading our machines. Right, now how does all this relate to our Gigahertz and rPerf ratings? So this is the magic secret chart. It is actually available. It's in a energy scale for Power 9 white paper web page. It's not like a document you can download. It's just a web screen. And here you can see this is this block over here. This is the old S924. The default is dynamic performance rather than maximum performance. And in here we can see the ranges that we've been quoting for the dynamic and the maximum. And then we have the nominal frequency here. A lot of commands, if you're on an AIX, you ask it for the frequency. It actually hands you the nominal frequency and not the maximum frequency that you're actually running at the moment. We'll come back to that in a minute. All right, so explain some of these things in here. I've explained that one already. That's the old S9214. Then if we go over here, we got these range if we're in maximum mode, so we can get the performance up on the S914. Okay, these are the 6 models of the scale-out machines over here. I've got the enterprise versions coming up. The nominal gigahertz, already covered that, and this maximum range in here. Right, moving on. Let's place things which I think are on the next chart. There we go. So these 2 numbers in here and here are the nominal frequencies. They've got the maximum frequencies, 3.9 and 3.9. Same in here. Of course, if you're in dynamic mode, and things get hot, then it will slide down to nominal. And if you're in maximum mode and things get hot, it will slide down to the frequency with no name. That's what that one is there. Okay, which is higher than your nominal, of course, as we've seen in our diagrams. So to move on. Okay, here's the enterprise ones. Similar sorts of numbers. I've color-coded them to make them easier to highlight and things. So we have the nominal, the maximum, and the frequency with no name. In actual practice, the bulk of the time, you'll either be handed the nominal frequency or the top-end maximum frequency when you ask what frequency you're actually running at. So we have to be careful on that. Right, now I'm sure you've all joined me on Twitter, and I've put out some tweets on this sort of thing, trying to explain these earlier on in the year. We've practiced to run now at the maximum range, which is 3.8 to 4 gigahertz, depending on the chip. Other chips from other manufacturers, it's quite frightening. As their number of cores go up, the gigahertz goes down. Quite often we see Intel servers running at 2.4 gigahertz. And you think, well, that's a bit slower than 4. That explains why the Intels are so slow. And I call this normal gigahertz plus a bit of overclocking going on that we do while we're got the heat envelope is okay. But I'm told I'm not meant to use that overclocking word, but I'm afraid you can't avoid it in a lot of cases. The energy scales say that we run at full speed but lower the gigahertz if things get too hot, like your air conditioning fails, or you have a very large configuration machine and the air is quite warm. How to get things hot? Well, if you don't have the maximum number of CPUs and cores, if you don't have the maximum memory sizes in there and all the slots filled, if you don't have the maximum number of disks in the front of the machine for the machines that have those, and if you don't have the maximum number of high-speed adapters, a high-speed adapter is 40 gigabits a second or 100 gigabits a second, are the two high-speed ones, and you're not actually got a very big workload running, and your computer is computer room is not, the air conditioning is working, then you'll probably never get to a hot computer situation where the gigahertz will come down. And I know, I've tried. My early ship machines weren't full config, and I could never get them to overheat no matter what I did with them. So they always ran at that top gigahertz, maximum gigahertz rating. Now there is one quite some quirks in here on the AIX commands, and I'll come to those in a minute. Particularly Nmon gives you the nominal gigahertz. So you think you bought a 4 gigahertz one and it says 2.8, and you think, whoa, IBM's shipped me the wrong computer. But you've got to, once you know about these two different numbers, you can see what's going on. Right, what can we find out about what's going on? If we on AIX, this is actually a bit of script that comes out of my rPerf corn shell script. It's available on the web as a download. It's actually using the internal database inside AIX to get the number out, but it is the nominal frequency. So it'll give you this great big number, which is 3.2 gigahertz. Okay, but it doesn't tell you what you're actually running at the moment. If you run these two commands, lparstat or mpstat, rather than reading all those, show you little examples in here. So lparstat, don't type in lpstat. I keep doing that. My fingers won't add the AR. With the E option in here, then you get these extra columns in here, the frequency, and you can see this is the current gigahertz rating, and the 19% is in here, 119%. It's 19% overclocking on my machine, and this is an early ship one. This is just a regular 9824 S924 machine. The mpstat does a similar sort of thing, tries to break out the different CPUs in here. I only had one CPU in it, and we get the same sort of numbers in here. Now, these are not very good for long-term data capture, are they, or graphing? You run the command and you have to sort of do screen scraping. There's some blank spaces on these lines in here. And if you change a setting, you'll throw out an extra header for lines in here to tell you went from dynamic performance mode to some other mode. It's very difficult to scrape these numbers and get these numbers out. It's a bit of a shame because that's something that Nmon's doing quite well in the past, but it doesn't do at the moment. So Nmon doesn't give you that current CPU rating, only the nominal at the start. Very embarrassing. This is being fixed. The developers are going to put a fix into Nmon. Unfortunately, we won't get that fix this year. If you raise a PMR or support case, as it's now called, you may be able to get a fix for that. The best I could do is the LPAR stat can be told with these options here to provide an XML, and then you can grep for this NSP, the nominal speed percentage, and then you can get these lines out in here. So in here, this is 12% overclocking, for example. That's pretty painful. I've got a new tool that I've been working on recently. NJSON that provides JSON format, and that can give you the nominal and the current. And I could actually get write a little program that just outputs those two numbers at you, and then we could add those to the end of an Nmon data capture and get those data in the meantime until Nmon actually catches up. If you're interested in performance stats in JSON format, then it's open source NJSON, and here's a link, a little advert, blatant advert to one of my little projects I'm running. If you're on Linux on a native non-virtualized machine, like an AC92 or an LC922, then these all work, but not if you're on a Power VM LPAR. In that case, we're only getting what I think is the nominal megahertz number. I need to investigate that further, but I'm pretty sure it's just the nominal gigahertz in that case. Here's the picture for IBM I. I'm not an IBM I person. Jyoti is, and she has explained to me this is all business as usual for the IBM I guys. There's a particular software package called iDoctor, and it knows all about the gigahertz. I can extract that at the System Activity Reporter is working. You can do this, and there's collection services can get the similar sorts of numbers out as well.
Indeed. Nigel, sorry, there was a question a little bit earlier, which was to do with migrating from Power 8 to Power 9 using live partition mobility or offline migration. What is needed to do to leverage the maximum out of the Power 9? LPAR profile CPU mode, for example?
Okay, well, if you're on Power 8, I'll assume that you've got SMT8 set for your LPAR. You can change that dynamically, so yeah, and why wouldn't you? You might get a little bit of performance boost from that. And you, of course, you'll be running in Power 8 mode because that's the highest mode, processor mode that you can get on a Power 8 machine. So you do live partition mobility over to Power 9. You'll be running on a Power 9 processor, but in Power 8 processor mode. You'll benefit from everything I've talked about here, apart from some of the new instructions that are available in Power 9. And the very latest versions of the operating systems, if you start them up in Power 9 mode, they can operate the computer slightly differently, looking at interrupt vectors and things like that. But you will be benefiting from the extra strength SMT threads immediately, so you'll get the vast bulk of the rPerf numbers benefit moving up. If you want the last 5% randomly chosen small number, then you could stop your LPAR once you're on Power 9 and restart it in Power 9 mode. You will have to be running something like AIX 7.2 TL3, which has been out a week or something, and then it can make use of some of the Power 9 features. Also, your applications, if they're Power 9 aware, then they can be using some of those special instructions to turbocharge their application. There's some applications, I know the SAP guys, for example, are very keen on tuning, extreme tuning. So they'll be providing a POWER9 aware version of their software. So if it starts up on POWER9, it can pull in some extra features for performance. If it starts up on a POWER8, well, you just don't get those extra turbocharger features. Does that answer the question? I hope so. Ask it again if I haven't.
Thank you, Nigel. There is another question which goes right back to slide 43. We'll take it at the end.
Okay.
Oh, and one more just come in. Only AIX 7.2, or will 7.1 get an update for POWER9?
7.1, that ancient version of the operating system. Yeah, then exists about 6.1, 5.3, and all that sort of stuff. No. As far as I'm aware, yes, if you want to use POWER9 features, you get the POWER9 performance. If you want the specific POWER9 features, then yes, you have to be on AIX 7.2 TL3 or above, which is just out. So don't expect many applications to be supported on that yet, but that's the way I think it's going to go. Having said that, they do get some pressure to backport some of these things, but well, at the moment, no.
Could we get AES numbers?
AS?
AES. I'm not sure what that is.
No, please clarify your question.
Open speed. Okay, we'll take that at the end as well.
Okay, well, we're nearly there now. I decided not to show you 25 more slides, which works better if you're interactive in a classroom, because we can take bets on, I make this change, what would you expect to see? So I tried to do it in one chart in here. So I've got an SIM24, 16 CPUs, so it's got 2 processors in the sockets, 8 cores each. The room temperature is a nice cool 22 centigrade. I haven't got much memory, a quarter of a terabyte of memory. It can get up to 4 terabytes, of course. I've got 8 disks in the front, but I'm only really hammering a pair of them in the VO servers. I've got 4 simple disks, nothing esoteric in here. And the nominal is 3.3 gigahertz. If you look at your NMON, that's the number it's going to give you. And the maximum is 4 gigahertz, so it can look quite low in here. So I started using the lparstat command, and I have to be quite honest, I was shocked. 2.3? How on earth can it go that slow? So I went around double checking, and I must have done this weeks ago, switched on the idle power saving mode. So you can see it's quite a jump down, and you can see it's running at 69% of the nominal gigahertz rating, taking it down to 2.3. Well, I thought, well, okay, I'll show them that. That's a good way of seeing it in operation. I was just running one application. It's one. It's a very small LPAR, and you can see in here this is a spinning. This is yes outputting into dev null, right? It's just spinning on a CPU, but it doesn't actually look like that very much, does it? It says that the user, for the utilization number is 32%, and idle is 67%. This is trying to show you that you're using the first thread, but if you use the other 7 threads, there's 67% of that single CPU is available, is still available. So you have to get used to that. The core is 100% used flat out in its LPAR, but it's trying to highlight the fact that there's some spare capacity in here. Okay, so I'm in power saving mode, and it was there for a long time. I've been on holiday for 3 weeks. If I then ran the application in here, and it immediately jumps up to, well, it's 4 gigahertz is the official max number. I get to 3.9. It could be like a rounding error. It could be 3.99 or something in here, but that's what I get. And we go up. So you can see it takes a little while to come up, a couple of seconds in here, and we get to 19% overclocking, which is really quite nice. You'll also notice in here, this is, I hadn't seen this before yesterday. Power is, the mode is called static, which is this nominal frequency with the idle power saving switched on, so it goes below that. Here it's gone to dynamic performance mode. This should be saying max performance mode, but again, we'll need to get that fixed. On a scale of 1 to 10, if the mode on the screen is not right, but the computer is doing the right thing, that's good enough for the first release, isn't it? Okay, notice the utilization numbers in there. I switched off power saving mode. Well, that doesn't affect anything down in here. Carries on running at 3.9 gigahertz. Then I stop the workload, and here you can see it's 100% idle. It's not actually running the LPAR at all. It'll be coming in for like 5 microseconds every second or something, just ticking over the interrupts. But again, it's gone right up to the maximum gigahertz rating, which is quite nice if we're running at the maximum number all the time. If we have just occasional little transactions come in, rather than being running at a 2.3, and then it'll say, "Oh, crumbs, there's some work," and over the next couple of seconds, put it up to the 4 gigahertz, and by which time the transactions disappeared. Then we actually did the transaction at 2.3 gigahertz. But if we're running at 4 gigahertz all the time, then we run those little transactions at 4 gigahertz, just about twice the speed. So that's a pretty good story. So you can see these are the things going on. There's a few little things we got to fix up in these sorts of things. I've had already people buy a machine and use N1 and said that the nominal frequency isn't what I paid for. But we can quickly test that with the lpar stat command. N1 will be improved to cover these things, and I've got my other tool that I'm working on to report them as well. Okay, so there's some extra things in here that I haven't really told you. If you're in maximum performance mode and 4 minutes, which is a tunable number, of whole server idle, practically nothing happening on the machine, then it will go into power saving mode. If we're in the dynamic performance mode, then a couple of seconds on a particular core, I think it was core, then it would dive down to power. So it's much more proactive, getting you down to lower gigahertz and saving electricity. As things get busier and busier, as we move across the chart, then this number will come down. I'm not telling you where that will start to come down. This line might be right over here, but it will lower the gigahertz if the temperature is going up, if you've got a full config on the machine. In maximum mode, as we get busier and busier and the machine gets warmer, the fans will pick up and be running harder, making sure your temperatures inside your box don't rise too much. And this point in here, of course, is arbitrary on my diagram in here. If you haven't got the full config, like we were showing in this previous chart, then we got right up to 100% busy and still running at the full gigahertz value. So you may not ever see this gigahertz being reduced to stop the machine overheating in a lot of configurations and workloads. So maybe I've overcooked worrying people about this. In actual fact, you may not see these things going on, but it's good to know that they're there to save the computer if you're getting into difficulty. Okay, so why no gigahertz reduction? Well, 8 cores instead of per chip instead of 12, there's less heat we generate. What's about a third, isn't it? A quarter. My computer is nice and cold, so when the fans are running at their regular speed, plenty of air going through the machine. Some CPUs might be at 99% busy and not other ones, because it's one LPAR goes busy, but the other 3 may not, and that'll be enough to keep the computer cool. If you haven't got the full memory size and full memory load, when in our bigger machines we get a 64 terabytes, that's an awful lot of memory chips, and they do take on the E980 several kilowatts of electricity, so it's like a 5-bar electric fire inside the kick, and we've got to push all that heat out. Also, when you load up memory, you're flipping those bits very fast, then they do warm up again, but if you're not hammering lots of memory, then you don't get the heat. For the machines like the S924 can have up to 18 disks along the front. Disks are pretty hot. More importantly, the discs block a lot of air coming in the front of the machine where they're situated. I tend to be using a lot of fiber channel SAN disks, so they're further down the computer room, not heating up my individual computers. And yeah, unfortunately my manager won't buy me some esoteric adapters, 40 gigabits per second or 100 gigabits a second, so those ones can generate quite a lot of heat. The actual processor on the adapter card is doing a lot of work at that very high speed, so it can generate some heat as well. If you had a load of those in the back of your computers, then again adapters hide a lot of the air escaping holes at the back, and then they actually generate heat themselves. So the service processor then decides, well, it's safe to run unless all of these are the opposite of what we have in my little computer. Then we can just run at the max gigahertz right up to the 100% flat out workload of my CPU's air memory. So here's my conclusions. I will read these out because we've covered a whole bunch of things in here, and it might generate some more questions. Spectre Meltdown, small hit. Phew, that's a relief, wasn't it? It just shows some good engineering going into our computers, that we're actually doing things very quickly, so if we do them a little bit slower, it's not a big hit. Energy scale is using these variable CPU frequencies to maximize the performance, and that's expected norm. You know, if you go back to Power 6, you know, you'd be running at, I think that one actually ran at 4.2 gigahertz, and it was just 4.2, and it would run that all day long. It wouldn't start running them slower for any reason, where we're more proactive slowing them down if we've got rising heat inside the computer. Massive jump in the rPerf numbers, but you do need to be running those SMT threads and force that by reducing the VPs and the entitlements. Watch out for the S914, I've hammered that often enough. And if you're not the full config, less than 100% busy, you may never see the reduction of gigahertz. I still think it's good to measure the gigahertz rating, just because you know, you might, the worst case scenario, users might complain on a Friday that the computer's running slower, and that's because, you know, the workload's gone up, but then the gigahertz has to come down 10% or something to cope with that. Yeah, with POWER9, use the SMT8. We've already covered that. I like monitoring my computer room, the room temperature. We use a Raspberry Pi to measure the room temperature, and we use the HMC REST API to get the temperature out of the scale-out machines, and the E950, the E980 won't give you temperatures, which is annoying, to be honest. But then it's a big machine. It's got 5 CECs, isn't it? 4 CECs for the CPUs and memory, and the system control unit. Exactly what is the temperature? Well, there's 5 temperatures. Well, no, if you look around the motherboard, it could be 10 temperatures in each one, so you've got 50 temperatures, and you know, there's no such thing as the temperature of the computer in that case. I think the idea is, if you've got the E980s, well, you should be running a computer room that has temperature monitoring, and you should be having, for your electrical input, measuring your with intelligent PDUs how much electricity they're taking, and with our room we actually have a Raspberry Pi measuring the temperature with probes around. You can have some of those sorts of things as well. That's on my Air Expert blog. And I think we should be measuring the gigahertz these days in number 7. And we all need to focus on removing those ghastly, horrible single-threaded applications. They're a curse. We need to get rid of them. And I don't have a lot of sympathy if you're stuck with one. Go and find another vendor that doesn't do these crazy things, because there's no way you're going to ever get those going faster. Right, I'm done. Any more questions, Jyoti?
There are a couple questions. If anyone's got more questions, please type them into the chat window and we'll take them now. Okay, there was one question, but I think you answered it already. So here we go. Using SMT8 instead of SMT2, are there changes needed in the application? And if yes, how much work can that mean to a big enterprise, or is it just changing the SMT setting on the machine and that's it?
The answer is yes and maybe and a bit. So going to the computer and changing the SMT rate, the maximum SMT that it can see is 10-second operation. You just run a command, SMT control on AIX. I think the same on Linux. And everybody should really set it to SMT8, in my humble opinion. There are some horrible workloads that don't like that, but most people should be running at SMT8, because otherwise you're hiding features that could give you an extra performance that you don't really want to do. Some applications, of course, I'm just trying, can't really think of an example, have tuning options on the number of threads the application runs. You could say for the database, the back-end processes are multi-threaded, and you tell it how many threads you want the back-end database to actually run. It's usually like in a config file. So when you start up the application, it says, oh, you want me to go 28 threads in here because you've only got 3 chips or something, and 8 threads each. So that's one way of doing it. Some databases, I believe Oracle these days, you can dynamically change that, and it will start up more threads or close down threads as they become idle, and change the amount of threading it's actually doing. Some applications like databases, you can have parallel queries that you can use multiple threads at the back end. But most online databases have lots of users, and each user is a different session, and each session is a thread. So if you've got 28,000 users logged in, then you've got 28,000 threads running inside your relational database management system, which is naturally threaded, if you like. If you have an application that is single-threaded and changing it to multi-threaded, yes, that can be quite a lot of work. There may be some natural ways of doing things if you've got multiple users, or maybe you'd have to change the algorithms drastically to break down large single-threaded, single set of actions to be done one after the other, to split these out so you can have pipeline it, so you have one thread doing the initial investigation of the problem, the next thread is working out what it wants to do, the next thread actually doing the work, and the next thread reporting on the results or something, and then the next thread returning the results back to the user or something. You've got 5 threads. That will take quite a lot of work to reorganize your application to do that. But your application vendors had 25 years to do this. Yeah. There's no excuse. Okay, there are some brand new exciting applications coming out, particularly in the Linux and open source world, where the guys developing it are doing it on a PC, and they're thinking, let's do the quickest, dirtiest job we can do to get the application working because we want to sell this. They may be doing it, but when they get up to serious enterprise class, then they have to rethink the way they do their application and re-engineer, and that can be a significant amount of programming effort. It also gets particularly tricky for debugging as well, if you're multi-threaded.
Thank you. Another question, we were talking about this earlier, Nigel, but it's come to me privately. Is there much difference between using DDR3 and DDR4 memory on POWER9?
Yes. Well, all right. The only machine you can do that on in POWER9 is the E980. The others are DDR4 memory only, and you can't move it up from POWER8 to POWER9 if it's DDR3. So that's the only case. In that case, Jeff Stutley, we mentioned, is Mr. Memory. He designs the memory for Power systems going forward. He's probably already got it sorted out for POWER10. He's working on POWER11. In the case of the E880 and E980, the E880 started with DDR3 memory and then moved to DDR4 memory. DDR4 memory comes, what's the advantages of going to DDR4? They take slightly less electricity, so that can reduce the power requirements and save some money, and reduce the heat inside the computer, which is a good thing, but it's small. It's not a major, not half or anything like that. DDR4, maybe slightly because of the electrical factor there, can actually go up to bigger DIMMs. So if you're stretching out 16 terabytes to 64 terabytes, then you need much bigger DIMMs, and they're only available on POWER9 in DDR4. But if you're not stretching the size in here, you're sort of half filling your memory, then Jeff Stuteley was very, very clever in his design of the Centaur Level 4 memory cache controller, so that the processor talks Centaur protocol to the Level 4 memory cache controller, and then the Centaur chip actually deals with the grubby real memory, the DDR3 and the DDR4, and that's what allowed us to have DDR3 and DDR4 in the POWER8, the E880 and E880C. So we can actually bring those over because in the POWER9 we're actually using the same Centaur memory controller. They may have updated it slightly, I don't know, but it's the same core piece of technology, so it can run DDR3. But you can't buy DDR3 memory for POWER9. You can only get it if you've bought a POWER8 and you're migrating it into POWER9. One way of doing it is moving it between a POWER8 machine and POWER9, or you've asked for a sort of model upgrade, and so you're upgrading your POWER8 machine with memory to the POWER9 machine, and you want to reuse the memory. So that's the way of doing it. It's not going to give you, as far as I'm aware, a performance benefit. For example, if you like, the performance of the back-end chips is hidden by the Centaur memory cache controller, and it's doing caching, which is far better than the memory can do in giving you back data. So there's not a speed disadvantage. We were talking earlier about this. You could get your DDR3 memory from POWER8 to POWER9 if that's the way you want to do it. I don't think it will be available in POWER10, so it's not going to you can't pass your DDR3 memory onto your grandchildren in the future products. I doubt it's going to be supported up to moving to yet another generation. And who knows, in 3 years' time, memory might be quantum or something. I don't know, some fancy new technology we haven't even seen yet.
Thank you. There's some other questions come through, and we'll take a couple more of those, and I'll stop the recording, and then we'll continue, if that's all right.
Okay.
One NMON question, if you're willing to answer it. Are you planning to implement real-time NMON to DB functionality so we can monitor AIX system in real-time mode in Grafana or any other web GUI monitoring tool?
I didn't pay Ivan to ask that question. The answer is yes and no. This is what my NJMON is doing. So it collects all the data like NMON does, but saves it in JSON format. Then JSON format, if you're not aware, is very, very easy to deal with if you're running a Python program. The Python has a data structure called dictionary, which it basically is JSON format. So if you get Python to parse, 20 megabytes of JSON data, it does in a split second because it just whacks it straight into a data structure. Then it's very easy in Python to pull out the information you want. So with NJMON, we can capture a JSON file. There's a lot more stats than NMON provides. It's the first thing. It runs on AIX, the VIO server, where there's more data for the virtualization resources. NJMON runs on Linux as well, on Power and Linux on Intel, and ARM, I presume, as well, just to compile. Then you run a Python program that can insert it. At the moment, we're handling InfluxDB, and Grafana will talk to an InfluxDB. It's just a time series performance data database, and we can then use Grafana to pull the data out. That works very nicely. The nice thing is the what I call the injector that takes the JSON file and puts it into InfluxDB is like 40 lines. You just literally pick up the JSON file, slightly format it for the InfluxDB injection, and then just pass it straight in. So you can do that. And we're also got that working with Splunk. It's another famous machine data analyzing and graphing tool out there. And the other one is haven't got working yet, but it's on the radar. Is log stash and Elasticsearch. Quite difficult to say those. So that'll be on the radar as well. So I'm already very excited about this. This has now gone open source and publicly available. It's on the same website as Nmon on SourceForge. So there was a URL on one of the pages in here. I sneaked it in because I like to talk about these new things. Now, if that allows you to save JSON format, you could also pipe njmon, pipe it straight into the injector and straight into the databases, InfluxDB or Splunk, all the new ones. So that gives you semi-real times, but it's not like, well, I worked on real time, which was down to microseconds behind reality sort of thing, but this will be typically for these sorts of online tools, you're collecting data every 30 seconds or something like that and putting it into the database. And then your Grafana, very nice tool for graphing data, will just update your screen every 30 seconds as the new data arrives. As you can tell, I like talking about this. What's the next question?
Okay, so I'm going to stop the recording there just to let people know that I haven't got anything more scheduled at this moment, but we're looking at possibly doing a session on VIOS, the new release 2.1. So if you'd like to hear more about that, do let me know, and I'll schedule such a session later in the year. That's it from a recording point of view. I'm going to stop the recording, but we'll stay on to take further questions.